welcome back. Today we're going to continue our exploration of matrices and introduce a special type of matrix known as the symmetric matrix and a closely related matrix known as the Hermitian matrix. So first off, let us define what we mean by a symmetric matrix. So let us first assume that the entries associated to our matrix A all belong to the set of real numbers, and let's assume that the transposition of matrix A is equal to the original matrix A. That is, if we switch the position in row I and column J, that's the same as row J column I in terms of the values of those elements. That is, Aij is equal to Aji for all J and I in their respective domains. For example, I is equal to 1 to n, and j is equal to 1 to m for an n by n matrix. So we say that A is said to be a symmetric matrix if it satisfies these properties. In particular, if A transpose is equal to A, then A is a symmetric matrix. So let's just look at a very quick example, in particular a 2 by 2 matrix A, which is given by 5, 7, 7, and 3. So if we look at the diagonal entries, notice that that's going to be A11 and that's going to be A22. So A11 is equal to A11 and A22 is equal to A22 by default, so the diagonal entries should be equal to one another when you take the transpose of that particular matrix. So they're not going to change, so we don't need to worry about them. What we need to worry about in terms of is it a square matrix or not is the off-diagonal entries. So it does A12 equal to A21. In this case, the answer is yes. Therefore, this matrix, when we take the transpose of it, is equal to the original matrix. Therefore, A is a symmetric matrix. Okay? So that's how we can test, at least element-wise, whether it is a symmetric matrix or not. Right. So now what I want to do is introduce several different theorems associated to symmetric matrices that are definitely going to be useful in some upcoming theoretical applications. So let's introduce our first theorem that we're going to be working through the proof of. So theorem number 1. So if A and B are symmetric, so let's assume that A and B are both symmetric, then the sum of those symmetric matrices also is symmetric. That is, if you take any two symmetric matrices, when you add them, you get a resulting matrix, always. So how can we go about proving this? So remember, the definition of a symmetric matrix is when you take the transposition, you get the original matrix. So notice A and B are given to be symmetric matrices. That means we have A transpose is equal to A, and also B transpose is equal to B in our toolbox. So using these, what can we get out of them? So let's take the transpose of this matrix A plus B and see if it gives us A plus B back. So A plus B, the transpose, is equal to what? So by properties of transpositions, transpositions can distribute over sums and also differences. That means this is going to be equal to A transpose plus B transpose by the property of transpositions. So we already know that A is a symmetric matrix, therefore A transpose is equal to A. B also is a symmetric matrix, therefore B transpose is also equal to B. Therefore we have that A plus B transpose is equal to the matrix A plus B. That means A plus B is a symmetric matrix, which is what we sought out to prove. So that theorem isn't too bad, and also it's going to come in handy in a couple other theorems as well. So theorem 2. If A is a symmetric matrix, so if A is a symmetric matrix, then A squared is also symmetric. And one should be able to also show that in order for a matrix A to be symmetric, it has to be a square matrix, right? Because keep in mind, if A is not a square matrix, then A squared, at least on the surface, does not make any sense in terms of how to calculate A squared. But if it's a square matrix, then A squared perfectly makes sense and is well defined. So, proof. So what are we given as an assumption? So we're given that A is a symmetric matrix. That means we know that A transpose is equal to A. So from this, what can we get out of this in terms of A squared? So we know that A squared by definition is going to be equal to A times A, right? That's the definition of A squared. So from this, what is the transpose of A squared? So the transpose of A squared is going to be the transpose of A and A. And we know that that's going to be equal to A transpose times A transpose. Now, I just want to make things subtly clear here. This A is not the A directly underneath it. This A is actually that A, and that first A is equal to that A. Yes, I know that A commutes with itself, but generally speaking, if it's AB transpose, is B transpose A transpose, but in this case, it doesn't really matter. So we have A transpose times A transpose, which is the same as A transpose the quantity squared. So if we sort of think about what we have here, what is A transpose? Well, A transpose is just going to be equal to A, because A is a symmetric matrix. Therefore, we have that A squared transpose is equal to A squared. Therefore, a matrix transpose is equal to that matrix. Therefore, A squared is a symmetric matrix, which is what we sought out to prove. Right? So that actually isn't too bad. Now, one may also guess, well, if A squared is symmetric, what about A cubed, A4, and so on? So one can prove this corollary if one wants to call it that. So if n is a natural number and A is a symmetric matrix, then A to the power of n is also symmetric. So if you know mathematical induction, that shouldn't be very difficult to prove. Next theorem of interest. Suppose we have the following. So if A is any square matrix, then the matrix A plus its transpose is always a symmetric matrix, even if A itself is not symmetric. Now this may, at least intuitively, come out as a little strange, but actually let's see if this is actually true. So A is any square matrix. So let's assume that it's, for example, a square matrix, say an m by n matrix. Now we're not going to assume it's symmetric because that's not in the premise of this particular theorem. Now let's look at this matrix A plus A transpose. So our claim is that this is a symmetric matrix. So if we take the transposition of A plus A transpose, we should get A plus A transpose back again. So let's see if we do. So A plus A transpose, the transpose, remember, by properties of transpositions, this is just going to be equal to A transpose plus the transpose of A transpose. And we know that A transpose is just A transpose by itself, and the transposition of itself is going to be equal to A. Now we know addition is commutative for matrices. That means this is the same as A plus A transpose. So we have that a matrix transpose is equal to that matrix. Therefore, A plus A transpose is a symmetric matrix, even if A was not assumed to be a symmetric matrix, which is actually pretty interesting. Now let's take a look at the next theorem that we want to prove today. And this theorem is actually quite important. So A is symmetric if and only if the inverse of A is symmetric, provided that A is an invertible symmetric matrix, that is. Okay, so let's see if we can go ahead and prove this, and let's actually work with the forward direction. So we're going to assume that A is an invertible symmetric matrix, and we're going to try and prove that its inverse is also a symmetric matrix. So we're given that A is symmetric, so that means we have at our fingertips that A transpose is equal to A. Let's also keep in mind that since A is invertible by assumption, that also means that the inverse exists and satisfies A times A inverse is equal to the identity matrix, and that's also equal to the inverse times that original matrix as well. So what I want to do is I want to actually take the transpose of that particular matrix and see what comes out of it. So A times A inverse transpose, because I need to show that A inverse transpose is equal to A inverse. So I need to introduce the transposition over the inverse in some way. So by properties of transpositions over products of matrices, we know that this is going to be equal to A inverse transpose times A transpose, which is just going to be equal to the inverse of A transpose times A transpose. But we know that A is a symmetric matrix, therefore this is going to be equal to A inverse transpose times the matrix A. Okay, so one can also show that this is also equal to A times A inverse transpose is equal to the identity matrix, right? Because remember, A times A transpose is equal to the identity matrix, right? So that means this quantity is also equal to the identity matrix as well. So we have that this is true, and also this is true as well, right? So from this, what can we say? So we have that this matrix times A is equal to the identity. Also, that matrix A times that matrix is also equal to the identity. So that means that A inverse transpose is the inverse of A. So how do we write this in symbols? That means A inverse transpose is equal to the inverse of A, which means the transposition of a matrix is equal to that matrix itself, which proves that A inverse is a symmetric matrix. Right? And that concludes the proof of that quite interesting theorem. Next theorem, so theorem number, let's call it 6. If A is any matrix, then A transpose A and also A transpose are always symmetric. And this is going to be very, very handy for some analytical tools when we start talking about decompositions a little bit later on. So how do we go about proving these? So let's focus on A transpose A. So let's take the transpose of it and show that it's equal to A transpose A. So that's going to be equal to A transpose times the transpose of A transpose, and that's going to be equal to A transpose A, which is equal to the original matrix, so that checks out. So if we do the same for the other matrix, A transpose, what is that going to give us? So A transpose, the transpose of it, is going to be equal to the transpose of A transpose times A transpose, which is just going to be equal to A transpose, which is the original matrix that we started with. And that concludes the proof for all of them, which relies on the product rule for transpositions. Now, I want to actually talk about the dimensions of A transpose A and A transpose for an arbitrary matrix A. In particular, the following also holds that A transpose A and A transpose are always square matrices, even if A is not a square matrix. So let's assume that A is an M by N matrix. So that means the transpose of A is going to be an N by M matrix. So if we look at the product A transpose A, that's going to be equal to a N by M matrix times A, which is an M by N matrix. So that's going to result into what type of matrix? So it's an N by M times M by N. So that's going to be equal to N by N matrix as well. And also if we look at A transpose, that's going to be equal to A, which is an M by N matrix, times A transpose, which is an N by M matrix. So that's going to be an M by N times N by M. So that's going to be equal to an M by M matrix. So if we look at a numerical example of what's going on here, so let's assume that A is a 5 by 3 matrix. That means A transpose A is going to be equal to what type of matrix? So it's going to be an N by N matrix. So that's going to be the number of rows times the number of rows. So that's going to be a 5 by 5 matrix. And A transpose is going to be the number of columns times the number of columns matrix. So that's going to be equal to a 3 by 3 matrix, right? So that's going to be equal to, wait a minute, that's a little backwards, isn't it? Yep, that should be a 3 by 3. It's 3 by 3 and a 5 by 5 because M is equal to 5 and N is equal to 3, right? So it's number of columns times number of columns. So that's going to be a column by column, and that's going to be a row by row matrix, right? I should have used just the theorems we just derived just a moment ago. But that's actually pretty interesting because even if A is not a square matrix, A transpose A and A transpose are always going to be a square matrix. And that's actually going to come in very handy when we start talking about decompositions such as eigenvalue decompositions and singular value decompositions a little bit later on. The next thing I want to look at is known as the Toeplitz decomposition for a square matrix A. So one can show, provided that A is a square matrix, that the Toeplitz decomposition of A always exists and is of the form half of A plus A transpose plus half of A minus A transpose. So what's so special about this decomposition? So we've already shown that A plus A transpose is always going to be a symmetric matrix. Even if that matrix A is not a symmetric matrix, it literally can be any square matrix, right? As long as A is square, A plus A transpose is going to be defined and is also always going to be symmetric. So what about this A minus A transpose? What is so special about that? So let's actually take a look at what A minus A transpose actually looks like. So if we have A, which is said to be, let's actually look at just basic 2 by 2 matrix. And we look at the transpose A transpose, which is going to be equal to 1, 3, 2, 4. And then we look at A minus A transpose. That's going to be equal to what? So that's always going to produce zeros on the diagonal, and then we're going to have 2 minus 3, which is equal to negative 1, and then 3 minus 2, which is going to be equal to 1, right? So we have that type of matrix. Now, is that matrix a symmetric matrix? No, because the off-diagonal entries are not equal to each other, but they're opposites of each other, right? So this is what we refer to as a skew-symmetric matrix. So let's actually go ahead and define that. So a matrix, let's call it A, is said to be skew symmetric if the transpose is equal to the opposite of the original matrix. So one should be able to show, at least from the definition of skewed symmetric, that the diagonal entries, so if A is skew symmetric, so if A is skew symmetric, then the diagonal entries of A must be equal to 0, right? Because that means the values on the diagonal and the values of its opposite diagonal have to be equal to each other once you transpose the original. And the only way that they can be opposites is if it's equal to 0 originally, right? Now, one can show also, and this is going to be the next important theorem, that A minus A transpose is always a skew symmetric matrix, provided that, of course, A is a square matrix. So how are we going to go ahead and prove that? So if we look at A minus A transpose, if we want to show that it's skew symmetric, that means we need to take the transpose of it and show that it's equal to the opposite of the original. So by the properties of transpositions, that's going to be equal to A transpose minus the transpose of A transpose, which is going to be equal to A transpose minus A. So if we factor out a negative 1, that's going to give us A minus A transpose, which is equal to the original matrix on the inside of the brackets. That means that concludes the proof that A minus A transpose is always skew symmetric, provided that that is a square matrix. So therefore, let's actually go back to the Toeplitz decomposition of matrix A. So the Toeplitz decomposition of a matrix, which was equal to 1/2 A plus A transpose, and then plus 1/2 A minus A transpose. So what it actually does is it takes a matrix A and decomposes it into a symmetric matrix and a skew matrix and the linear combination thereof of a symmetric matrix and a skew matrix. So that's pretty much what a Toeplitz decomposition does, and we'll look at a couple applications of Toeplitz decompositions a little bit later. The next occurrence of symmetric matrices actually comes in multivariate calculus. So let's assume that we have a multivariate function f whose partial derivatives are denoted by partial f with respect to xi. Then the Hessian matrix, or just the Hessian of f, is defined by this n by n matrix, where n is the number of variables that f has. So f is a function of, for example, x1, x2, down to, say, xn. So if you're only working with a function of 3 variables, then the Hessian of f is going to be a 3 by 3 matrix. And what exactly does the Hessian matrix of a multivariate function consider? So notice that these are all second order partial derivatives. In particular, this one is the second partial derivative with respect to x1 twice. That's the second partial derivative with respect to x2 twice, and that's the second partial derivative with respect to xn twice, and all of the other crossed off diagonal entries are the mixed partials with respect to, say, xi and xj. Now, let's also bring back an important theorem from multivariable calculus, and that's usually called Clairaut's theorem. So, Clairaut's theorem. Some people will also call this Schwarz's theorem. So, if all second order partial derivatives are continuous, then HF transpose, i.e. the transpose of the Hessian matrix, is equal to the original Hessian matrix, i.e. the Hessian is a symmetric matrix. So the Hessian is a symmetric, those are some strange looking M's, is a Hessian matrix, symmetric matrix. So, what does that exactly mean? That means if you take the partial derivative with respect to x2 followed by x1, or you do the partial derivative with respect to x1 first followed by x2, you should get the same exact function provided that the partial derivatives second orders are all continuous. Let's do a quick example of this, just in case you don't remember, say, multivariable calculus. So, quick example. Let's assume that f of two variables, so this is a three-dimensional function, is equal to x cubed plus 5x squared y plus 3y squared. Let's take some partial derivatives. So let's take the partial derivative of f with respect to x. So that means all the y's are constants. So that's going to give us 3x squared plus 10xy, and then 3y squared is just a constant, so that differentiates to 0. And the second derivative with respect to x, so we take the derivative with respect to again, that's going to give us 6x plus 10y. And what are we going to get next? So let's do the partial derivative with respect to y. So that's going to give us, so x cubed again is a constant, because we're taking the derivative with respect to y, not x, partially. And then y, again, x is a constant, so that's going to be a constant, so that's a constant times a linear function, so that's going to be 5x squared. And the derivative of 3y squared, that's going to give us 6y. And if we take the second derivative, or the next partial derivative with respect to y, that's going to give us, well, 5x squared disappears, and we're just going to be left with 6 there. And now, let's take the partial derivative of x with respect to y. So what I want to do is I want to take the derivative with respect to y partially of that expression. So if I take the derivative with respect to y of that, that's actually going to give me what? So 3x squared disappears, 10x is a constant, y is a linear function, so that's just going to give us 10x, and you can show that if you take the derivative with respect to x of that expression, you actually get the same exact thing. So that means that's going to be fxy, because notice that the second order partial derivatives, 6x plus 10y and x, and also the mixed partials are all continuous functions, so that actually they give us the same exact function there. So here are our second order derivatives. Notice that this actually counts twice because we have fxy and fyx. So now that we've calculated all of our second order partials, we can construct the Hessian of that particular function. So the Hessian matrix of f is going to be equal to 6x plus 10y. So that's fxx. Then fxy is going to be equal to 10x. fyx is going to be equal to 10x, and then fyy is going to be equal to minus 6. And notice that this is a symmetric matrix, and one could also, of course, consider the determinant of this Hessian matrix and its applications, but we'll talk about them at another time. Now that we've discussed some properties associated to symmetric matrices, let us take this up another level and consider the complex analog of symmetric matrices, which are known as Hermitian matrices. So now, instead of letting the elements of our matrix A be real numbers, now we're going to consider these elements to be complex numbers. And let us assume A satisfies the property that the transpose of A, in addition to the conjugate of each of those elements, is equal to the original matrix A. If that satisfies, then we say that A is a Hermitian matrix, and we'll sometimes write that AH is equal to A. That is, the Hermitian of A is equal to the original. So one could also consider that AH is sort of like the complex conjugate transpose of the original matrix. So let's just do a quick example on calculating the Hermitian of a matrix, and then we can easily verify if that matrix is Hermitian or not. So let's assume that A is the 2 by 2 complex matrix given by 3 plus 2i, 5 minus 3i, 4i, and minus 7. And keep in mind, if you don't know what I is just the square root of negative 1, but you can sort of think of it as a variable in its own right. So once we take the transpose of this, the transpose of that is going to be equal to what? So the diagonal entries are going to remain fixed, and the off-diagonal entries are going to switch positions. So we're going to have 5 minus 3i in that position and 4i in that position. Now what we're going to do is we're going to take the conjugate of each of those elements. So all our imaginary portions of our complex numbers are going to be negated. So that means 3 plus 2i is going to change to 3 minus 2i. 4i is going to change to minus 4i. 5 minus 3i is going to change to 5 plus 3i, and minus 7 is not going to change because the imaginary part is equal to 0. And we can also write this as AH. So then we can look at this original matrix A and the Hermitian of that particular matrix, and we can compare. Are these matrices the same exact matrix? Obviously not. Therefore, we can conclude that A is not a Hermitian matrix, right? Which is kind of a sad day for A, I guess. Now, one thing that must be true, maybe you can see it from this example, notice that the diagonal entries will not change positions when you take the transpose of it. And in order for A to be Hermitian, the conjugate of those diagonal entries must be equal to the original, which means that the imaginary portions of those elements must be equal to 0 for that to hold. So that gives rise to this next theorem that actually always holds for Hermitian matrices. So let's call this, say, theorem number 8. So if A is a Hermitian matrix, i.e. A is equal to the conjugate transpose of A, then the diagonal entries, each of them, belong to the set of real numbers, i.e. their imaginary parts are equal to 0, where k is equal to 1, 2, down to, say, n, the number of rows and columns of that original square matrix A. So let's see if we can go ahead and do a nice little proof of this. So let's assume that A is a Hermitian matrix. So if A is a Hermitian matrix, that means A, say, ij, is equal to the conjugate of AJI. So the transposition and the conjugate, right? And for diagonal entries, that means I is equal to j, right? Because when I is not equal to j, that's the off-diagonal entries. So that means AII is going to be equal to AII conjugate, right? So let's actually define AII to be equal to the real part of A plus the imaginary part of A, right? And here the subscript I is not the complex number I, but I there is going to be the complex number. So once we do that, we're going to have what? So the conjugate of II is going to be equal to xi minus IYI, right? So if those two are equal, what does that give us? So that means x, the real part of the diagonal entry, plus I times the imaginary part of the diagonal entry must be equal to the real part minus I times the imaginary part. So we can solve this and get some identities. And also we can divide both sides by I because I is not equal to 0, so they cancel. So we're left with yi is equal to minus yi, which means that 2yi is going to be equal to 0, which means that yi, which keep in mind is just the imaginary part of the diagonal entries of h, right, is equal to 0, right? And if the imaginary part is equal to 0, that means the diagonal entries of h all belong to the real numbers, which concludes the theorem that we're trying to prove. So if you do not have real numbers on the diagonal of your matrix, it is impossible for that matrix to be Hermitian. So those is just some important properties and theorems and a couple little side applications associated to symmetric and Hermitian matrices. Hope you enjoyed, and I'll see you in the next video. Take care.